Let's finish worksheet 8. So number 4, radius of a sphere increases at a constant rate of 2 centimeters per minute. At the time when the volume of the sphere is 40 cubic centimeters, what is the rate of increase of the volume in cubic centimeters per minute? So here's our volume formula. We're trying to get to dV dt. So let's see. We have the radius of the sphere increasing at a constant rate. So radius is going to get larger over time, so we have to make sure that dr dt is a positive value. Volume of the sphere is 40 cubic centimeters. However, there's just a moment in time. What is the rate of increase of volume? Find dV dt. Okay. So we have to start with the volume formula. V is equal to 4/3 pi r cubed. And let's see, we can find the derivative. So I'm going to jump ahead and look to see what we need. So dV dt, we find the derivative. It becomes 4/3 pi times 3r squared times dr dt. The 3's cancel out, so we're left with dV dt is equal to 4 pi r squared dr dt. Okay. We're trying to find dV dt. We have dr dt, but there's another variable that's not quite found yet, right? We don't know what radius is. However, we do know what volume is. All right, we know volume is 40. So we can use this information to find out the radius at this moment in time. So so back to here, 40 is equal to 4/3 pi r cubed, and I can solve for r. Okay, divide both sides by 4/3 pi, which same thing as multiplying by 3/4 pi. 40's cancel out. Take the becomes 30 over pi. To get r by itself, I take the cube root of both sides. So r is equal to 2.122. Okay, so I have my value for radius. So now 4 pi r squared times 2. Multiply all this in your calculator. You're going to get 113.124 cubic centimeters per minute. Okay, number 5. If our function is differentiable, differentiable function with 1, -3, and 5, 4, which of the following must be true? Now, we can think of these as endpoints, and we see that this is potentially referring to mean value theorem. Okay, so I just drew a graph of something that could occur. One of the conditions is already met for, two of the conditions actually have been met for mean value theorem. Okay, differentiable function, which also means that in order for a function to be differentiable, it must also be continuous as well. So it's able to state two things with just that statement. So if this problem could be potentially referring to mean value theorem, let's go ahead and find the slope between the endpoints. Okay, so change in y over change in x, 4 minus -3/4, so we get 7/4. So we know through mean value theorem that if the average slope is 7/4, then the instantaneous rate of change must be equal to 7/4, because we've already been established that this function is differentiable. So that matches option E. F prime of k is equal to 7/4 for some k between 1 and 5. This is going to be true because of mean value theorem. Okay, 6, 7, and 8 refers to the graph on the left. At which point do both dy dx and d2y dx2 equal 0? This refers to the slope. Okay, this refers to concavity, right? This is notation second derivative. So where is the graph going to be concavity being 0? So in other words, where the graph is neither concave up nor concave down, and where the slope is 0. So if you look at the graph here, there's a couple of points where the slope is 0, at Q, at R, and at T. However, at Q, this is concave up, so that's we can't use Q as an answer solution. T is part of concave down, so we can't use that as well. But if you look at R, R has slope of 0, but then it's also neither concave up nor concave down, so therefore answer choice R. Okay. At what point is dy dx positive and the second derivative equal to 0? So we want a slope of that is positive, but then also where the graph has concavity of 0. So in other words, we're looking for potentially a point of inflection where the graph changes from concave up to concave down. So we look at where slope is positive. So the only points where slope is positive, at point P, slope is not positive. This slope is 0, that slope is 0. So, and the only point that we can think about is point S, right? So point S, we see that the slope is 0, but then also concavity is equal to 0 because this is a point of inflection, right? We have concave up transitioning to concave down, so that transition point is point of inflection, and point of inflection has concavity value of 0. Okay, number 8, at what label point is dy dx equal to 0 and d2y over dx2 negative? So we want a graph that is where the slope is 0 and then also part of a concave down graph. So again, slope of 0 is at Q, R, and T. The only point where we have concave down is going to be at T. Okay, so answer choice E. All right, for 9, 10, and 11, we're going to be referring to the velocity graph on the left. So number 9, for how many values of t in the interval from 0 to 6 is the acceleration undefined? Okay, so the acceleration is going to be undefined. We're looking at the velocity graph, so it'll just be where this graph is not a smooth curve. So at 3 and at 5. Okay, so if you think of acceleration as simply the slope of velocity graph, then you can just look at where the slope doesn't exist. So at 3 and 5. Okay, number 10, during what time interval is the speed increasing? So speed is increasing when acceleration and velocity have the same signs. So let's create a sign line for velocity. So for velocity, we see that velocity is going to be 0 at 3, and then this portion is above the x-axis, so this is a positive velocity, and then here we have negative velocity, so we can put that on the sign line. Okay, for acceleration, we're looking at the slope. Right, so for acceleration, the critical points will be at 3 and at 5. These are where, so remember, critical points can either be where the slope is 0 or where the slope is undefined. So for acceleration in this case, critical points will be at 3 and 5. And remember, acceleration is simply the slope of velocity. So here we have negative slope, so we know we have negative acceleration. Here, negative slope, negative acceleration, and from 5 to 6, positive, so therefore positive acceleration. Okay, so the only time where the speed is increasing is where they have the same signs. So the only time where they share the same signs is between 3 and 5. Right? Between 3 and 5, both velocity and acceleration will have negative signs. At all other points, there are going to be velocity and acceleration will have different signs. So answer choice B. Okay, number 11, what is the average acceleration during the first 5 seconds? So average acceleration is simply the slope of velocity, right? Average acceleration, so we find the average slope between the two endpoints for velocity, right? Average acceleration is simply change in velocity over change in time. So we're looking at the velocity graph. We can find the ordered pairs for velocity, so 5, -2, and 0, 3. So if we just find the change in velocity over change in time, so v5 minus v of 0 over 5 minus 0, so we get -5 over 5, so that's going to get us -1. So average rate of change will be -1.